Question 3. A model rocket is launched at an angle of 40 degrees to the horizontal with an initial speed of 100 meters per second. Determine the time it takes to reach its maximum height, and we've got to assume there's no air resistance. The first thing we have to do is change that velocity vector, which has got a magnitude of 100 meters per second at an angle of 40 degrees, into its corresponding horizontal and vertical components. So we're going to have a horizontal component, which we don't really need to work out in this diagram because we've been asked to find the height we go, so we're dealing with the vertical initial velocity, and that's represented by that blue arrow there, that blue vector, and that's the triangle we have, 40 degrees with the horizontal and the vertical components. So I can redraw that here, and the one we're looking for is a vertical component, and we know that the speed of the actual rocket is going to be 100, so that side of the triangle is going to be 100 meters per second. So the vertical side here is going to be 100, and it's going to be multiplied by sine of 40 degrees. So that gives us a initial vertical velocity of 64 meters per second. And that's the one we're going to use, because that's going to be the initial vertical velocity when the rocket is launched. Now all we have to do is put down our kinematic characters. We have the initial vertical velocity, which we just worked out to be 64 meters per second. Our final velocity, well, at the top of its flight, the maximum height, the vertical velocity is going to be 0. So that's going to be our final vertical velocity at the maximum height. UVA is acceleration. As always in these diagrams, we're taking up to be positive and down to be negative, so the acceleration due to gravity is 9.8 minus 9.8 meters per second every second. S is what we're really after, and T, well, that's not going to come into it at this moment, so we can leave that blank as it stands. So from all our data, you can see we've got U, V, A and S. So we've got to use the equation with all those characters in it, all those variables in it, and we choose this equation here, V squared equals U squared plus 2 times acceleration times the displacement. Now we're after the displacement, so if we have to rearrange that equation, and you have to practice this, if I take the U squared over the other side, I'm going to get V squared, take away U squared, I'm going to put that in a bracket, and that's going to go to twice the acceleration times the displacement. To find the displacement on its own, I've got to divide by 2a, so I've got to get V squared minus U squared, and I have to divide that by 2 times a, 2 times acceleration. That's going to give me the displacement. So now all I have to do is put in the numbers in for it. The final velocity squared is going to be 0, so it's going to be 0 squared. Take away an initial vertical velocity is 64, and we're going to square that, and divide by 2 times acceleration, 2 times, remember it's minus 9.8. So if we do that in our calculators, we're going to end up with a value of 200 plus 208 meters, so that means that the maximum height reached by the rocket is 208 meters. Question 5. Two spacecraft approach each other as shown in the picture. They dock together, which means they join together. Determine the speed and direction of the combined spacecrafts after docking together. First thing we do is draw a diagram what's happening. We can use boxes to represent the spacecraft. That's the spacecraft coming from the left to the right, and that's the spacecraft coming from the right to the left. So what we got here, we have got the following information. We know it's going to be travelling in this direction, and it's going to have a, first of all, a speed of 8 meters per second. And we know it's going to have a mass of 500 kilograms. So that's information for that one. We know the other spacecraft is going to be travelling in the opposite direction, going from right to left, with a speed of 10 meters per second. And it's going to have a much bigger mass, a double mass of 1,000 kilograms. So that's the situation before. Then if we look at the situation after the two spacecraft dock together, we'll have this situation here. We'll have a combined mass this time, assuming no mass falls off. It's going to be 1,500, so 1,500 kilogram mass. And we don't know where the speed is, so we won't even put an arrow in for that. We'll just say that the speed is v, and we'll have to work out the mass of that to give us the direction in which the spacecraft are going. So our first then thing to do is to work out the momentum before, and that's this up here, the total momentum before. And remember, the momentum is equal to the mass times the speed of an object. So we look at, first of all, we'll call these objects P and Q. So we'll just call this object here P, and we'll call this object here Q. So first of all, we have the momentum of P. So we'll write down momentum of P. I'll just write M for short, momentum of P. And that's going to be equal to 500 mass, 500 times 8. And we can put the answer down. 500 times 8 is going to give us 4,000. And it's going to be in the right direction, we can see up here. Now the momentum of Q will be in the opposite direction, but we'll let the maths work that one out. It's going to be 1,000 times minus 10, because it's going in the opposite direction, going from the right to the left. So that's going to give us minus 10,000 units of momentum. Remember, the units of momentum are kilograms, meters per second, but I'm just going to leave that out now to make our table look quite okay. Therefore, I say the total momentum before the collision is equal to the sum of 4,000 and add on a minus 10,000, which is going to give us minus 6,000 units of momentum. Now, what about after the collision? Well, after the collision, we're going to have a combined mass of 1,500 kilograms. So the total momentum after the collision is going to be equal to the mass, 1,500, multiplied by V. And we don't know what V is, so we're just going to have to have an algebraic expression, 500 V. But what we do know is conservation of momentum. That's the key factor here. Conservation of momentum. And what that really means is the total momentum before is going to equal the total momentum afterwards. So the total momentum afterwards should be exactly equal to the total momentum before. So what's the total momentum afterwards? It's 1,500 times V, and that should equal to exactly minus 6,000. We have to keep in the minus signs. So therefore V is going to equal to minus 6,000 divided by 1,500. And if we do that in our calculators, we end up with minus 4 meters per second, which means that the whole combination of the docked spacecraft is going to move in that direction from right to left, because it's minus, with a speed of 4 meters per second every second. 4 meters per second. And that's how we do the momentum problems. Stick to it very closely and have your stuff organised out, and also make up the wee table, total momentum before, total momentum afterwards with your diagrams, and then that's the most important line, conservation momentum, total momentum afterwards is total momentum before, and equate the total momentum before with the total momentum afterwards, taking into account the negative, because it's going in the other direction, momentum is going from right to left, it must be negative, and we get our final answer.